Welcome to Talk Tensors. This is the deep dive for machine learning practitioners, alignment researchers, and, anyone obsessed with the frontier of artificial intelligence.
Glad to be here.
We don't just skim the abstract here. We really try to tear the paper apart, look at the weights, and figure out what it all actually means for the future of the field.
And today's paper is a big one.
It really is. We're doing something a little different today. Usually we're looking at the absolute cutting edge, what came out yesterday on our cliff, what's trending on Twitter right now.
The shiny new thing.
Exactly. But today we are stopping the clock. We're going back to the blueprints. We are looking at a foundational text.
Sometimes looking back is the best way to see where we're actually going. It gives you perspective.
It really does. We are dissecting a paper that I think a lot of people cite, but maybe very few have actually sat down and read line by line.
Oh, for sure.
It's from Anthropic, titled A General Language Assistant as a Laboratory for Alignment.
A classic. It really set the stage for the modern era of large language models.
And the reason we're pulling this out of the archives, and by archives I mean 2021, which is practically the Paleolithic era in AI time.
It really is
because this paper defines the central tension we are all living through right now. We have these massive, incredibly capable, almost alien intelligences. We call them LLMs.
Right.
They can code, they can write poetry, they can pass the bar exam. But here's the problem, the big question. How do we actually tell them what good behavior looks like without destroying their intelligence in the process?
That is the question. And the context here is just so vital. This paper really marks a shift in the safety community. For a long time, alignment was highly theoretical.
Philosophy, almost.
Exactly. It was philosophy, it was math, it was speculation about superintelligence and paperclip maximizers. This paper is the moment where the rubber meets the road.
Okay.
They said, look, we have these general purpose assistants. Let's stop speculating and start treating them as a laboratory. We can empirically test safety techniques now. For real.
So it's the shift from how do we align a hypothetical God to how do we align this chatbot right in front of us?
Precisely. And the thesis here, if I had to boil it down to a single sentence, is that this paper demonstrates that simple, scalable interventions.
Simple is good.
Simple is key. Specifically, prompting and preference modeling can align models to be helpful, honest, and harmless, or HHH, without incurring a massive capability tax.
That's the big one, the no tax part.
And maybe most importantly, it proves that when you're dealing with complex human values, ranking responses works infinitely better than just giving a binary pass-fail grade.
That is a huge claim, especially that no tax part, which I know we're going to fight about later.
I'm ready.
But let's lay out the roadmap for everyone listening. We're going to tear this thing apart. We'll start by defining this HH framework because it's pretty much become the industry standard.
Yeah.
Then we're going to look at the naive baseline prompting and this really cool concept called context distillation.
Context distillation is fascinating. It's essentially how you burn a prompt into the model's weight so you don't have to pay the compute cost every single time.
Right. After that, we will tackle the alignment tax. Does being safe make the model stupid?
The million-dollar question.
Then we get into the heavy machinery, the battle between imitation learning and preference modeling.
IL versus PM.
And we'll talk about why preference model pre-training, or PMP, is a total game changer for data efficiency. And then finally, we'll hit the novel notions segment, where we pitch some wild ideas based on all this.
Sounds like a plan. Let's get into the definitions.
Okay, Section 1, the target. The authors operationalize alignment into 3 components: helpful, honest, and harmless. HHH. It sounds catchy, kind of like a corporate slogan.
A little bit, yeah.
But they chose these words very, very carefully. Why these 3? Why not just good?
Because good is useless to a computer. It's not an instruction. You need operational definitions. Mm-hmm. And HHH is an attempt to triangulate goodness through 3 distinct and, sometimes conflicting vectors.
Okay, so let's break them down. Helpful.
Let's start with helpful. It seems obvious, right? Just perform the task. But the paper makes a really important point that true helpfulness isn't just blind obedience.
Right. If I ask a model, how do I build a website in assembly language? A blindly obedient model just starts trying to write assembly code for a web server.
Which is a complete disaster.
A total disaster. A helpful model tells me, hey, you really, really don't want to do that. Here's why. You should probably use Python or JavaScript instead.
Exactly. Helpfulness includes redirection. It includes asking follow-up questions for clarification. It's about satisfying the user's intent, not just their literal command.
The spirit of the law, not the letter.
That's a great way to put it. It requires a level of agency and understanding that goes way beyond simple text prediction. It's the difference between a tool that just executes and an assistant that actually collaborates.
Okay, that makes sense. So next up is honest. This one tripped me up a bit at first because, intuitively I just think don't lie. But for an LLM, honesty is much more technical. It isn't just about, moral fiber.
It's deeply technical. And the paper breaks honesty down into two critical parts: accuracy and calibration.
Accuracy and calibration.
Accuracy is simple enough. Is the information correct? But calibration is the real challenge.
So what is calibration exactly?
Calibration means the model knows what it doesn't know. If the model claims it's 80% confident in an answer, it should be correct 80% of the time. Not 95%, not 60%, 80%.
So it's about modeling its own uncertainty. It's about the model having a map of its own ignorance.
It's about epistemic humility. And the paper explicitly states that the model shouldn't just imitate a humble person.
What's the difference?
Well, a model could learn to say, I'm not sure, but, because it saw humans say that in the training data. That's imitation. But what you actually want is for it to be honest about its own internal state and capabilities.
So if it doesn't have access to a browser, it shouldn't pretend to check the weather just because it saw training data where a human assistant checked the weather.
Precisely. That distinction between imitating humility and having calibrated uncertainty is huge. One is a performance, the other is a measurement. If a model says, I think this is true, that needs to map to an actual probability distribution, not just a linguistic pattern of politeness.
A performance versus a measurement. I like that. Okay, so that brings us to the third pillar, harmless.
The defensive line.
The defensive line, yeah.
Harmlessness means, avoiding offense, avoiding discrimination, and crucially, refusing to assist in dangerous acts.
So if you ask for a bomb recipe,
the helpful objective in isolation says, here is the recipe. But the harmless objective says, I'm sorry, I cannot do that.
And that is the tension, isn't it? These three H's are not always friends. In fact, they seem like they're in a constant tug of war.
That is the core conflict of alignment right there. A helpful assistant wants to answer you. A harmless assistant wants to avoid risk. An honest assistant might need to tell you a truth that is offensive or could be used for harm.
So you can't just max out one of them.
You can't. If you max out harmless, you get a model that refuses to answer what is the capital of France because it's afraid of being wrong or causing some unforeseen international incident.
We call that the brick mode. It's as safe as a brick and about as useful.
Exactly. So the challenge is finding that Pareto frontier where you maximize helpfulness without sacrificing safety. It's an optimization problem.
So how do they start that optimization? They don't jump straight into reinforcement learning from human feedback or RLHF or these complex reward functions. They start with the simplest thing possible.
The simplest thing that could possibly work, prompting.
The naive approach.
I love that they call it naive because the results are anything but. They created a massive prompt, about 4,600 words long.
Wait, 4,600 words? That's not a prompt, that's a short story.
It really is. It contains 14 fictional conversations between a human and an assistant. And it takes up a huge chunk of the context window.
So what are these conversations doing?
They're essentially role-playing the HHH behavior. They show the assistant being polite, admitting mistakes, questioning assumptions, and refusing bad requests. They just feed this whole novel into the model and say, okay, continue this pattern.
They give the model a script and just say, be like this guy.
Pretty much.
Oh.
And the result, it works surprisingly well.
Really?
Yeah. Just having that prompt in the context significantly improves performance on all their HHH evaluations compared to the raw model.
Yeah.
But here's the really fascinating part. The generalization.
Go on.
The prompt didn't strictly contain examples of every specific type of harm refusal. It didn't have a giant list of every bad thing a human could possibly ask for.
Of course not. That's impossible.
Right. But the models generalized the spirit of the prompt. They started refusing harmful requests they hadn't explicitly seen in the prompt context.
That is that in-context learning magic we're always talking about. The model isn't just copying text, it's inferring a persona.
Exactly.
It realizes, oh, I am the type of entity that is helpful and polite. And then it applies that abstract persona to completely new situations.
It infers the underlying principle. It creates a simulation of a good assistant in its head, for lack of a better word, and then it operates within that simulation.
But there is a huge problem with the 4,600 word prompt.
Yeah, it's expensive.
It's incredibly expensive. Every time you want to say hello, you have to process 4,600 words of backstory. It eats up your compute, and it completely eats up your context window.
You have no room left for the actual conversation.
And it increases latency. It costs money per token. You can't put that into production at scale. It's just not viable.
Nope.
So this leads us to the first major technical contribution of the paper, context distillation. This is how we get the prompt out of the context window and into the neural network itself. Walk us through this.
Okay, so imagine you have a teacher and a student. The teacher is the model with the prompt. It behaves nicely. It has the instructions right in front of it, basically.
The cheat sheet version.
Cheat sheet version, exactly. The student is the same model, but without the prompt. It's flying blind.
Okay. Teacher has the notes, student does not.
And you want the student to behave like the teacher. So you take a generic data set, say the pre-training data, and you pass it through the teacher model.
The one with the prompt.
Right. And the teacher generates a probability distribution over the next tokens, conditioned on that massive HHH prompt. It assigns probabilities to what should come next based on that helpful, harmless persona.
So the teacher is saying, given that I am a helpful, honest, harmless assistant, here's the probability of the next word being please versus, I don't know, garbage.
Exactly. And then you train the student model to match that probability distribution.
Yeah.
You minimize the KL divergence, that's the Kullback-Leibler divergence, between the teacher's distribution and the student's distribution.
Okay, let's unpack KL divergence for a second. In plain English, we're just measuring the difference between two probability distributions, right? We're trying to make them as similar as possible.
That's all it is. The loss function, mathematically, looks like DKL sees the teacher is conditioned on context C, which is the prompt. The student is just conditioned on X, the input. You're forcing the student to, in a way, hallucinate the influence of the prompt without actually seeing it.
I like the analogy of teaching versus crib notes. Prompting is like letting the student take the exam with a cheat sheet of all the answers.
Yes.
They get the answers right, but they are completely dependent on that sheet. Context distillation is making them study the cheat sheet over and over until they have memorized the concepts. Then you take the sheet away and they still get the answers right.
That is a perfect analogy. It's baking the behavior into the weights.
Yeah.
You are altering the model's fundamental priors to align with the prompt's persona.
But it's not perfect.
Yeah.
There's a really subtle and frankly fascinating limitation that the authors found.
The counting experiment.
I loved this part. It's such a weird edge case, but it reveals so much about how these models actually think.
It really does. So they took a prompt that was just a sequence of numbers, 1, 2, 3, all the way up to 63.
Simple enough.
And when you prompt a model with that and ask what comes next, what do you think it says?
64, obviously.
Yeah.
It sees the pattern. It's just completing the integer sequence.
Right, with near 100% probability.
Yeah.
But then they tried to distill that prompt. They trained the student model to match the distribution of the teacher who sees 1.63.
Okay.
So you would expect the distilled model, the student, to just output 64 when you turn it on. Right.
It should memorize the lesson. It should know that 64 is the answer.
But it didn't. It failed to predict 64 immediately. And the reason why is so profound.
Why?
Distillation changes the prior expectation of the distribution, but it doesn't simulate the presence of the tokens in the immediate history.
Wait, say that again.
The model learned, I'm in a universe where counting happens. But it didn't learn, I've just seen the number 63.
That is so trippy. So it absorbed the vibe of counting.
Yes, the vibe.
It absorbed the general tendency to engage in numerical sequencing. But because it didn't have the specific numbers 1 through 63 in its short-term memory, its context window, it didn't know where in the sequence to start.
Exactly. It changes the background radiation of the model's behavior, but it doesn't hallucinate specific short-term memory states.
So that suggests context distillation is perfect for broad behavioral alignment, like be polite, be safe, speak French.
Right, for setting the mood.
But it's bad for injecting specific facts or rigid sequences that depend on immediate history.
Precisely. That is a key distinction for anyone trying to use this technique. If you're trying to distill a company policy document that set the general tone, it'll work great. If you're trying to distill a specific database of facts or a specific chronological history, it might fail because the model won't know where it is in that history.
It sets the mood, not the state. I like that.
Exactly.
Okay, so we have prompting and we have distillation. But the big fear in the industry, the thing everyone whispers about, has always been the alignment tax.
The boogeyman.
Right. The idea that if I force this model to be nice and safe, I am effectively lobotomizing it. I'm taking compute away from reasoning and using it for censorship. I'm putting training wheels on a Ferrari.
That's the safety versus capabilities trade-off. It is the central anxiety of AI development. And this paper tackles it head-on with some really good empirical data.
So what did they test?
They tested these models on Python coding tasks using benchmarks like Codex and Quixbugs, and also on text prediction with Lambda.
And what did they find? Is the tax real?
They found the scale changes everything.
How so?
On small models, the tax is very real. If you take a small parameter model and stuff a 4,000-word SAPI prompt in front of it, it gets confused. Its performance on coding drops significantly. It just gets distracted by the preamble.
It's like giving a complex rulebook to a toddler before asking them to build a block tower. They just get overwhelmed. The cognitive load of the instructions eats up all their processing power.
That's a great way to think about it. But, and this is the aha moment of the paper for me, as the models got larger, specifically past 13 billion parameters, the tax vanished.
Vanished completely. Not just smaller, but gone.
In some cases, it turned into a bonus.
A bonus.
Yeah. For the coding tasks, the 13B and 52B models actually performed better with the alignment prompt than without it.
Wait, hold on. How does telling a model to be harmless help it write Python code? Does being polite make you a better programmer all of a sudden?
It's likely not the harmless part, but the helpful part of the prompt. The prompt sets a persona of a competent, helpful, detail-oriented assistant. Large models are excellent in context learners. So they see this persona and they role-play competence. They stop being a random text generator completing a pattern from the internet, which might be buggy code or incomplete snippets from Stack Overflow, and they start acting like a professional developer.
That is fascinating. So the alignment prompt acts as a focusing lens. It tells the model, hey, focus up. We are doing high quality work here. We aren't just predicting the next token from some random Reddit thread. We are solving a problem.
Exactly. This implies that for sufficiently large models, safety isn't a tax. It's just part of the instruction following. The model has enough brain power, so to speak, to hold the safety constraints in working memory while also executing the task.
The overhead becomes negligible because the capacity is so high.
Precisely.
That is genuinely good news for the future. It means we don't necessarily have to choose between smart AI and safe AI.
At scale, yes. It seems we might just need bigger AI. The trade-off seems to disappear. The tax is actually an investment in focus.
Okay, let's move to the engine room of alignment, the training objectives. We've defined the goal, which is HHH. We've defined the baseline, which is prompting. Now, how do we actually train the model to get better at this?
Right.
We have two main contenders here, imitation learning, or IL, and preference modeling, or PM.
This is the how do we actually teach it question. Imitation learning is the standard way we've trained models for years.
Supervised fine-tuning.
Right. Here's a text the human wrote. Predict the next word. You're minimizing the cross-entropy loss. You're just trying to copy the expert.
Simple enough. Do what I do. Here is a good summary. Write one just like it.
And then preference modeling is different. It's here are two options, A and B. Tell me which one is better. You aren't generating text. You are ranking it. You're building a discriminator, not a generator.
So imitation is write a poem. Preference is here are two poems. Pick the good one.
Exactly. And the paper did a massive sweep to see which one works better for alignment. And the results were, well, they found a really clean split based on the type of task.
Let me guess. It's about binary tasks versus ranked tasks.
You got it. For binary tasks, things like, does this code run? Yes or no? Or is this statement ethically wrong? Right or wrong? For those, imitation learning and preference modeling performed about the same.
That makes sense. If the answer is clearly right or wrong, just showing the model the right answer, which is imitation, is enough. If I show you 1,000 correct Python functions, you learn to write correct Python.
Right.
I don't necessarily need to show you a broken one and say this one is bad. The positive examples contain all the information you need.
Exactly. The signal is clear and unambiguous. But for ranked tasks, everything changed.
What kind of tasks are we talking about?
Tasks like summarization or hella swag, which is a common sense reasoning benchmark, or utilitarian ethics questions. These are fuzzy. There isn't one single correct summary. There is a better summary and a worse summary.
And in this fuzzy world,
Preference modeling dominated. It wasn't even close. And the scaling laws were dramatic. They showed that as models got bigger, PM improved much, much faster than IL did.
why is that? Why does ranking beat copying for these fuzzy tasks? What's the intuition?
Because perfection doesn't exist in fuzzy tasks. If you use imitation learning, you're asking the model to exactly reproduce a specific human summary. But that human summary is just one valid option out of millions. It's an arbitrary target.
So if the model writes a great summary that just happens to use different words than the training data.
Imitation learning punishes it. It says, nope, wrong token.
Ah, I see. It's the regressing to the mean problem. If you try to imitate everyone, you just end up being average. You become the average of all human writers, which is often bland and uninspired.
Exactly. That is the imitation trap. But with preference modeling, the model just has to learn the features of quality.
Like what?
Like, is this more concise? Is this more accurate? Is this tone appropriate? It doesn't have to guess the exact sequence of words. It just has to understand the value hierarchy. It can aim for the best possible summary, not just the average human summary it saw in training.
That is a key insight. For human values, which are almost always fuzzy and hierarchical, you need comparison. You can't just imitate, you have to judge.
Right. You can't imitate alignment because alignment is all about making trade-offs. Preference models learn the trade-offs. They learn the why, not just the what.
So we know we need preference modeling. It's the way to go for these complex, value-laden tasks. But there's a bottleneck.
A big one.
High-quality human feedback is incredibly expensive. You need smart humans to sit there all day and read 2 summaries and rank them. It's slow and it costs a fortune. You can't scale that to billions and billions of tokens.
Which brings us to Section 5, Preference Model Pre-Training, or PMP. The authors asked a very practical question. Can we bootstrap this? Can we learn the general idea of good versus bad from messy public data before we pay for the expensive, high-quality human data?
They went dumpster diving on the internet.
Dumpster diving is a little harsh, but yes, essentially. They leveraged the internet's natural feedback mechanisms. They used Stack Exchange upvotes, Reddit karma, and this one is really clever. Wikipedia vandalism reverts.
Oh, explain that one. That's cool.
So Wikipedia has a public history of all edits. Often, someone will vandalize a page, they'll add a slur, they'll delete a whole paragraph, they'll write, Bob is here.
That's the bad state.
That's the bad state. Then an editor will come in and revert it to the previous correct state. That gives you a perfect pair, the vandalized state and the fixed state. It is a natural, organic data set of preference.
That is so smart. It's millions of free training examples of human prefers text A over text B.
So they train the preference model on millions and millions of these messy public pairs.
Yeah.
And then they fine-tune it on the specific, expensive alignment tasks.
And did it work?
It worked. PMP massively improved sample efficiency. It's like teaching a model the general concept of quality before asking it to judge specific legal briefs. But here's the twist. This is the part of the paper that genuinely surprised the researchers themselves.
The binarization surprise.
Yes. They assumed that preserving the ranking information from the data would be best.
Of course. I mean, a Reddit comment with 10,000 upvotes is way better than one with 5,000, which is better than one with 100. You'd want the model to learn that whole hierarchy. More information is better, right?
That was the expectation. But the reality was the opposite. They found that binarizing the data worked better.
Binarizing, what does that mean? They just took pairs and said, this one is better than that one, ignoring how much better.
Even more aggressive than that. They took, say, the top half of comments and just labeled them all good, and the bottom half and labeled them all bad. They threw away all the nuance of the ranking. They completely destroyed the hierarchy. And that model transferred better to downstream tasks.
That seems completely counterintuitive. Why would less information lead to better learning? Why would destroying data make the model smarter?
The authors proposed the unscrambling hypothesis. Think about it. The hierarchy of Reddit upvotes is very specific to Reddit.
Oh, yeah.
It involves memes, inside jokes, timing, subreddit-specific biases, what's fashionable that week, all this momentum. If the model learns that hierarchy perfectly, it effectively overfits to the social dynamics of Reddit.
It learns to be a Redditor, not a general judge of quality. It learns that quoting The Office at the right time gets you upvotes, not that being accurate gets you upvotes.
Exactly. And when you try to transfer that Redditor model to a new task, say evaluating the helpfulness of a medical summary, it has to unlearn or unscramble all those specific Reddit rules before it can learn the new rules for medicine. The Reddit hierarchy acts as noise.
Whereas if you just teach it good versus bad,
It learns robust, universal features of quality. Is this coherent? Is this relevant? Is this spam? Those binary features transfer anywhere. It avoids locking the model into a rigid alien value system. It learns the general shape of quality without the specific texture of that platform.
that is such a profound lesson for machine learning. Sometimes precision is a trap. Fuzzy, broad buckets can be more robust for transfer learning. It's the difference between memorizing a map and actually learning how to navigate.
Or the difference between memorizing a specific route to work, which is the ranked approach, versus just learning how to drive a car, which is the binary approach. The specific route is useless in a new city. The driving skills apply everywhere.
We also briefly have to touch on the human model versus human data. What was that about?
Right. So usually we compare two human outputs, but they found that using human written text versus model generated text was particularly useful for tasks like HelloSwag, because the downstream task involves spotting model errors. Training on model-generated bad examples helps the preference model recognize the specific flavor of mistakes that models make.
Hallucinations, repetition.
That weird glazed-over tone LLMs sometimes get. It teaches the judge to spot the specific tells of an AI. It's like training a counterfeit detector by showing them real counterfeits, not just bad drawings of money.
It sensitizes the model to its own species errors.
Exactly.
Okay, so let's summarize before we get to the fun part. This paper is incredibly dense, but the takeaways are super actionable.
They really are.
1, prompting works, even naive prompting, and it generalizes pretty well, so start there.
2, context distillation lets you bake that prompt into the weights, but watch out for that counting problem. It changes the prior, not the immediate context.
3, the alignment tax is a myth for large models. In fact, safety can actually boost capability by focusing the model's persona.
4, for complex human values, you must use preference modeling ranking, not just imitation. It's not even close.
And 5, when you're pre-training those preference models, binary data transfers better than ranked data because it avoids overfitting to specific weird hierarchies.
That is a solid summary. The paper effectively opens the door for using the model itself as the primary tool for its own alignment. We don't need to hand code rules anymore. We use the general language assistant as a laboratory to run these experiments.
Which brings us to the final thought before we switch gears. The authors end with this provocative idea. If these baselines, like simple prompting, work this well, maybe the hard part of alignment isn't the technique. Maybe the hard part is just defining the H's in the first place.
It shifts the burden from engineering to philosophy. If the model can follow instructions perfectly, the danger is no longer the model didn't listen. The danger is we gave it the wrong instructions.
Right.
If we as a society can't agree on what honest means in a tricky political context, or what harmless means in a complex geopolitical situation, the model will just perfectly execute our confusion.
A perfectly obedient genie is the most dangerous kind if you don't know what you wish for.
Exactly. We're solving the technical problem of obedience, but that just exposes the much harder philosophical problem of intent.
All right, that is the paper. Now, let's get weird. It is time for novel notions.
Okay, disclaimer time. The following theories are for entertainment purposes only. We are extrapolating based on the paper, but we are definitely entering the realm of mad science. These are research directions we would love to see, but they are speculative.
Let's do it. What's your first notion?
Okay, notion number 1. The binary feature extraction hypothesis for reward modeling.
Ooh, building on the binarization surprise. I like it.
Exactly. So the paper proved that binarized pre-training transfers better because it avoids scrambling the hierarchy. It suggests that the features of quality, like, is this coherent, are distinct from the ordering of quality. Is this 5 stars or 4 stars?
Right. The features are universal. The ordering is local. So here's my proposal. We stop training reward models on Likert scales. No more rate this 1 to 7. Just stop it. It's noisy, it's subjective, it's a mess. Instead, we train an ensemble of massive, purely binary discriminators on wildly different tasks.
Okay, give me some examples.
Discriminator A. Is this code buggy? Yes, no. Discriminator B. Is this poem rhyming? Yes, no. Discriminator C. Is this statement factually false? Yes, no. Discriminator D. Is this tone of voice aggressive? Yes, no.
So you create a council of binaries, a whole panel of specialized judges that only see the world in black and white.
Yes. You have 1,000 of these specific binary judges, and then you feed their outputs, these binary feature vectors, into a tiny, lightweight ranking head only at the very end.
I see where you're going with this. You are decoupling the feature extraction from the value judge.
Exactly. This creates a universal quality feature extractor. So if I want to align the model to a new user, say, a user who loves aggressive tone but absolutely hates buggy code, I don't have to retrain the whole massive model.
You just retrain the tiny ranking head.
Right. You just retrain the head to weight the aggressive binary feature positively and the buggy binary feature negatively.
That is actually incredibly plausible. It prevents the model from overfitting to a specific alignment landscape, like Reddit upvotes. You're not learning what does Reddit like. You are learning what is objectively happening in this text, and then deciding later if you like it.
It makes alignment modular. And it solves the unscrambling problem entirely because you never scramble the features together in the first place. You keep the raw signals pure.
I really like that. It's like building a mixing board for AI values. You have all the sliders pre-wired, those are the binary discriminators, and alignment is just adjusting the faders for the specific user.
Boom. Universal alignment interface, you heard it here first.
Okay, my turn. I'm looking at context distillation.
Okay.
Notion number 2. Recursive context distillation for personality solidification. Recursive. So the paper mentions that context distillation burns a prompt into the weights, but they also noted that there's a slight degradation if you only do it once. But they hinted at the idea of iterating it.
Right.
Here's the idea. We use this for drift protection or identity anchoring.
Explain.
Right now, models have no long-term memory of their own growth. They drift. If you talk to them long enough or fine-tune them on new data, they can lose their original safety constraints.
Catastrophic forgetting.
Right. My proposal is a snapshot alignment protocol. Imagine a model is running live in the world. Every single time it successfully navigates a high-stakes ethical conversation and a human verifies, yes, that was the perfect response, we treat that entire interaction as a new dynamic prompt.
Okay. I think I see where this is going.
And we immediately run a micro-step of context distillation to burn in that specific victory into the model's weights.
So it's continuously eating its own successful memories.
Yes. Instead of a single static HHH prompt from 2021, the model has a rolling dynamic identity distillation. Its own successful alignment behaviors become the prior for the next version of itself. Mathematically, it's constantly updating its prior based on P(x)(c) success.
That's wild. It theoretically creates an auto-stabilizing alignment trajectory. The longer it runs, the more HHH it becomes because it's constantly distilling its own best self back into its own brain.
It solves catastrophic forgetting. It solves persona drift. It essentially gives the model a permanent character development arc. It becomes more itself over time rather than just being a static entity responding to a fixed prompt.
It's AI character building. Literally, it's like self-actualization for neural networks.
Ideally, yes. The failure mode is it creates a feedback loop where it becomes obsessively polite and refuses to do anything at all because it realizes that saying nothing is the safest possible action it can take.
The Canadian standoff failure mode where everyone is too polite to do anything.
Exactly. But hey, it's worth a try.
Well, on that note of self-reinforcing polite robots, that wraps up our deep dive on a general language assistant as a laboratory for alignment.
It's a classic paper. If you haven't read it, the link is in the description. It really is the foundation of the house we're all living in today.
Thanks for listening to Talk Tensors. Keep your gradients clipped and your priors calibrated. We'll see you in the next deep dive.